Ya, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My dear students, today we will learn about this topic about solubility. This topic is important in the study of pharmaceutical preformulation. So please kindly study these subjects. So we can give definition for this terminology, solubility as the ability of solutes to dissolve in solvents and to form a solution. Why this solubility is so important in these topics? Because in formulation, we have to characterize these properties, whether the drugs or drug candidate have good or poor solubility. And also, in order to be dissolved or absorbed by the body, generally a drug substance must be in the form of a solution. However, many drugs are formulated in solid form, maybe for the reasons such as its stability or easy in manufacture or easy in transportation, or maybe easy in administration. So that's why the drugs majority formulated in solid form, such as a tablet or capsule. So the understanding the solid state of the drug substance provide the basis for developing the forms. So it is important to understand this issue. First is the process of transition of drug from a solid state to a solution. And also we have to understand the difference between two kinds of solubility, thermodynamic solubility as equilibrium concentration, or also we have to understand the kinetic solubility as maximum concentration. So this is important to understand because this issue will necessary to be a tool for prediction and optimizing in vivo drug product performance. So this is the, once again, I want to say that many drugs formulated in a solid dosage forms for these benefits. And to be absorbed, this drug should be in a solution form. So that's why we have to understand this transition of solid to solution, and also two kinds of concentration, equilibrium concentration as a thermodynamic solubility, and maximum concentration is the kinetic solubility. So with understanding this issue, we can predict and optimize the in vivo drug product performance. Before we talk about the absorption, we have to understand many issues in solution, and for that we have to understand the solid state properties. So in drug development, around 40% of drug candidates discontinue due to poor solubility. And also there is a fact that 30 to 40% of drugs can continue to develop with the solubility under 5 milligram per ml, the PS7. And also the solubility also one of the fundamental properties in categorizing drug in a BCS system. BCS system can be defined as a classification of drugs based on the two properties. biopharmaceutical properties such as solubility and also related to the dissolution. And the second is permeability. So based on this system, the drug can be classified to be four classes. As you can see in this slide, BCS class 1, if the drug have a high solubility and also high intestinal permeability. Class 2, if the drug have low solubility and high permeability. For the BCS class 3, if the drug has high solubility and low permeability. And the last is BCS class 4, if the drug has a low solubility and low intestinal permeability. This is a notation that high soluble drug could be defined if the drug in a highest dosage strength can be dissolved or can dissolve in a less than 250 ml of water in a pH range of 1 to 7.5. Whereas the high permeable could be defined as if a drug has absorption rate in human in greater than 30% or 85% according to the latest WHO and FDA guidance. This calculation is based on mass balance analysis or based on the configuration to those administered intravenously. And also we know this classification, the degree of solubility that usually we can read in many compendia such as USP or pharmacopoeia, European pharmacopoeia or Indonesian pharmacopoeia. For example, in Indonesian pharmacopoeia, this category put in, I think maybe you can read in the third Indonesian pharmacopoeia, this category of solubility. For example, here if the drug categorized as very soluble, if the fat absorbance is less than 1, which means that the 1 fat absolute needs less than 1 fat absorbance, or the solubility range is over the 1000 milligram per ml. Yeah, pretty soluble here is we need 1 to 10 fat absorbent to dissolve 1 fat solute, or the solubility range is 100 to 1000 milligram per ml. And so on here. What is the connection between this categorized of the drugs based on this table and previously categorization in the BCS? So we can say that the drugs that are very potent, which means the strong inactivity, maybe in the application, in the dosage form is not require large doses. So the solubility problem, for example, the drug categorized as sparingly soluble or slightly soluble, but if in application is just only needs small doses, so the problem in solubility is not automatically become a problem in BCS system, especially in for bioavailability or effectiveness. So that's why we need to understand the classification of drugs based on the BCS, biopharmaceutical classification system. So now the first important step is how to determine the solubility of the substance or candidate drugs. If the solubility of the compound is very low or undergoes hydrolysis, for example, so the measurement of solubility is not easy. It is very complex, time-consuming, and analytically challenging. In the initial preformulation, Also, maybe we just get a small amounts, less than 50 milligram of the drug substance. So that's why we need the methods for solubility measurement, because also we have to, there is not guarantee if the drug has purity or also contain the polymorphic forms. And also in the solubility determination, we can predict by the computer modeling approach, such as these programs. And this is just only for prediction that we can use if this method validated experimentally. So here is the boundary of solubility. If the drug has solubility more than 10 milligram per milli, so we can say this preferred, the drug is preferred. Or the drug can be acceptable if it has more than 1 milligram per ml. But also we can state the problem for a certain drug if the drug has solubility less than 1 milligram per ml. So we need the effort in development, such as we can apply the source formation, or also we can apply another method, such as a new dosage form design. The dosage formulation is also have to consider to be simple as possible. So now we can talk about the solubility and dissolution. High solubility does not in itself indicate rapid dissolution. This means that if the solubility of drug is high, then the dissolution also rapids. Because solubility is the position of equilibrium, and dissolution is the process or the rate at which equilibrium achieved or occurred. This means that a drug substance with good solubility is not automatically good in bioavailability. It has been stated that absorption will not be inhibited based on the Kaplan category. If the drug substance has an IDR, IDR means intrinsic dissolution rate, greater than 1 milligram per minute per centimeter square, which means that if we have this value, then the drug will not get a problem in absorption process. But if the dissolution will be limited, if the IDR less than 1 milligram per centimeter square per minute, or in second unit is 0.0017 milligram per centimeter square per second. This is based on the Kaplan's theory. So this table also show that the relationship between IDR and classification in BGS system. For example, here ranitidine have IDR, which is very high, 43.1. So this drug can be categorized as a high soluble in BGS system. Other is metoprolol and propranolol, and so on. Nadolol, this is more than 1. So the BGS system categorizes this drug to be high soluble. But we can categorize further. It is class 1 or class 2 or class 3 or class 4. Class 4 based on the another properties, which mean permeability properties. For example, here for ranitidine, if the permeability value, intestinal permeability is more than 90% or 85%, so we can classify this drug ranitidine to be BGS class 1. Other drug, for example, is labetalol, cetopropen, furosemide, naproxen, and others. Has an IDR less than 1. So these drugs categorized to be low soluble in BGS system. So now we talk about the what is the intrinsic solubility. This is important to understand the kind of solubility. So we talk about the solid forms substance because this drug could be transformed to a solution. So now we talk about solubility, mean that the solute in a solid form dissolved in a solvent, so to be a solution. So well, first we have to understand the component of solid drug substance. Why the solid could be forms? Because this solid particle has a three-dimensional arrangement as a result of intermolecular bonds. The strength of bonds, which means the crystal lattice energy, control many physical properties of macroscopic crystals, such as hardness or melting point and others. And also, if the temperature of a solid increase, meaning that the energy also increase, energy content in that structure is also increased or high. From experience, if the temperature reaches a certain critical levels, which means the melting temperature range of the solids undergoes, the solid can undergoes a phase transition to form a liquid. Even maybe there is some another gas like barbiturates could be directly converted to the gases. We know this is the sublimation process. From a thermodynamic perspective, the internal energy of a solid, if we study about the thermodynamics, we can understand that in that internal energy in a solid, it is become or influence or related to the energy of the crystal lattice. Once again, that if the internal energy of a solid become greater than the energy of the crystal lattice, so the intermolecular bond will be breaks. So this is how the binding between molecular will be spared. The amount of energy or heat required to melt from a solid is known as enthalpy of fission. This symbol, delta HF, which means that the heat of enthalpy, enthalpy of fusion, and usually expressed in a unit of kilojoule or mole, kilojoule per mole or kilojoule per grams. If the molecules are able to align in different repeating patterns, which means there is a phenomena of polymorphism, then it is very likely that the strength of the intermolecular bonds and hence the energy of the crystal lattice will change. Therefore, two polymorphs of the same drug will have different melting temperature range and enthalpies of fission, and as a consequence, the physical properties will be different, including such as dissolution rate or thermodynamic solubility. By knowledge of the melting range and enthalpy of fission, this can be obtained from this instrument such as DSC, differential scattering calorimetry. This instrument can measure the melting range or also the energy of enthalpy fission of the drugs. So that's why these parameters are often the first to be quantified during pre-formulation. So now we look for the reaction of the solid form of the drugs that transition to a drug in aqueous form. So the solution itself is a phase transition with the drug changing from a solid matrix to a solid. For this phase transition to take place, this one, First is solid-solid interaction, and should be overcome in the sense of solid to melt. And then also there is a second process, second transition, solvent-solvent interaction that must be replaced by solute-solvent interaction. So there is two energy should be breaks here. First, the energy that bind the solid-solid interaction, and the second is the energy to break the solvent-solvent interaction, and then replaced by the solute-solvent interaction. So there is two energy at least that influence the strength of binding in solid forms. So assuming that an excess of solid is added initially to get the saturation, and then the solid is always present, and the equilibrium position will exist between the solid drug and solids. So we can write the reaction equilibrium like this. A drug in a solid forms will be equilibrium with the drug in a melt condition, and will be also equilibrium with the drugs in aqueous space. So the concentration of dissolved drug at this point is known as the equilibrium solubility. Only the term solubility is used here, also acceptable. Usually we just only call solubility. Solubility here is the equilibrium solubility. We usually name it this terminology as solubility itself. And the solution will be saturated. If a drug has an ionized group, then the equilibrium solubility of the non-ionized form, we call it as intrinsic solubility, or SO. So this is the point. This is important because if the drug is ionizable, it will ionize to a great or lesser extent with the pH of the solution, and this will affect the observed solubility. If the structure of the compound is known, then the compound must be clear. Whether the solubility will show dependence on pH. But if the structure is unknown, then measuring the solubility over the pH ring will show if any fat is ionizable. If the compound has an ionizable group, then the solubility modification by salts, it is become a possible formulation strategy. So from a thermodynamic perspective, the input energy required to break the solid-solid interaction that must be equal to the enthalpy energy of fission that it is process required for change from the melts of the solids, from the solid to the melts. We need the energy, namely the enthalpy of fission. So the second energy also necessary to break the interaction between solvent and solvent, then establish the interaction between solute and solvents. This is a new bindings that form the solution. The energy needed for this process known or called by the enthalpy of mixing. So in totally, the net enthalpy of solution, this means that the energy necessary to form the solution, delta H solution or heat for solution, is a summary for sum from two energy here, delta H, heat of fission, and heat of mix. This heat consists of the energy for breaking the solvent-solvent interaction, then the energy needed for compose or establish the interaction between solute and solvents. Then the solution could be formed. So from this equation, we can imagine that the solubility could be high or poor based on the how large the delta H sol needed to form the solution. So for the overall process, usually the intrinsic solubility is can be right in this equation. Ks is equal to the SO, and SO also equal to the X2. X2 is the mole fraction of the solutes. So from the summary here, first, solubility is the maximum concentration of a given solute that can be attained in a given solvents. Then the solid transition to solution, known as a dissolution process. It is the transition process from solid to solution, known as dissolution. And thermodynamic solubility is a position of equilibriums. When we can say the solubility means that in the thermodynamic terminology is the solubility in equilibrium condition. The solution governs the rate of which solubility is achieved. As a general rule, solubility below 1 milligram per ml is likely to hinder developments, while solubility above 10 milligram per ml is acceptable. So please study by yourself about the ideal solubility, the effect of temperature on solubility, and effect of pH on solubility, and also the solubility and physical forms. So I think in general sense that usually temperature, if the temperature is increased, then the solubility could be influenced by the temperatures, which means if the temperature increase, the solubility will be increased. It is the in general sense, but not valid for all substances. So please study about this. And how the effect of pH on solubility, I think I have explained in ionization concept that the drug which have the ionizable groups will be affected by the pH, in relation to solubility. And also how the physical forms influence the solubility. I think I will go to the last topics in the slides. Yes, you can read this explanation. So now I'm going to do the correlation between solubility and physical forms. Yeah. So if the drugs, two substances have the same enthalpy of fission, this is an equation to calculate the solubility based on the heat of fission and based on the temperature of medium environment and the melting temperature of the drugs. So based on this equation, we can predict that the drug substance with a lower melting point will have a greater solubility. Similarly, if two drug substances have the same melting point, their solubility depends on the enthalpy of fission. The form with the lower enthalpy of fission show the greater solubility. So here we have an issue that is very interesting, that the effect of polymorphism. How the effect of polymorphism on the solubility. The polymorphism is a phenomenon that the same substance can exist in a different solid state, or maybe we can say that the drugs have a different crystal lattice. The same drug, but have a different crystal lattice. In this case, the chemical properties of the molecule are the same, but the enthalpy of fission and the melting point will be different as a result of the difference in crystal lattice energy. Each polymorph must have a unique solubility. There is an exception in anechoic enantiomer condition. Usually, the stable polymorphs has the highest melting point and the greatest enthalpy of fission. Then will have the lowest solubility. If metastable forms has a lower melting point and the enthalpy of fission and greater solubility. The form with the lowest melting point and enthalpy of fission will show the greatest solubility, which is a binary of the amorphous forms. There is three categories of polymorphs: stable polymorph, metastable polymorph, and amorphous form. Between three kind of polymorphs, of course, the amorphous form has the highest solubility, the greatest solubility, because the amorphous form have no crystal lattice. So there is no in the delta H mix, which means that the heat of fission is lower for the amorphs compared to the crystal forms. A very important point to note here is that solubility is defined as the equilibrium between the solid and the solid states. Thus, if a saturated solution is prepared from the metastable polymorph for amorphous form and the excess solid are removed by filtration, the remaining solution can be considered saturated with respect to the stable forms. Eventually, the stable form will precipitate as the system establishes as a new equilibrium position. This is the figures explain how the equilibrium can be changed from the one condition to another condition. For example, here, this is between equilibrium, the solubility rate is very high. Then when the equilibrium achieves, the solubility will be stable here. But the equilibrium will be changed if there is a change in form of polymorphs, from the stable to metastable, or from the metastable to amorphs. There is a change in solubility. So now we come to the summary of these topics. The different polymorphs of a drug will have different solubilities. If the excess solid are removed from after equilibrium is reached, and the dissolved polymorph is metastable, the remaining solution can be considered saturated with respect to the stable, and crystallization will eventually occur. Solubility generally increases with temperature. Knowledge of the enthalpy of fission and melting temperature allow calculating the ideal solubility. Another issue is how to determine pKa from the solubility determination in different pH. So we can calculate this parameter. For example, here, what is the pKa of the weak base cordial epoxy given the following solubility data? If now on the SO is 2 milligram per ml, the ST means solubility total solubility at pH 4 is 14.6, and the total solubility at pH 6 is 2.13 milligram per ml. So based on this equation that derived from Anderson-Hasselbalch equation, we can use this equation pKa equal to the pH plus log ST min SO divided by SO. So this is the answer for this cases because the cordial epoxy is a weak base. So we can use this equation. pKa is pH plus log ST min SO per SO. At the pH 4, the pKa is 4 plus log 14.6 because it is the solubility in pH 4 for the ST. And the SO is same, yeah, 2 milligram per ml. So this pKa from the pH4, we can obtain 4.799. At pH 6, the pKa equal to the 6 plus log 2.13 to minus 2 divided by 2. We get 4.83313. So we can it is possible to make inference from to value. So the pKa is around 4.8. And this correspond to the literature value 4.8. So the conclusion is first, high aqueous solubility is clearly the preferred quality of a drug substance. But low solubility is not always a barrier to successful development because the formulation may be designed to aid solubility or drug might be very potent. So only low dose are required. Knowledge of the melting point and enthalpy of fission allow calculation of ideal solubility. Often the solubility in water is considered non-ideal, mainly because of the solid-solvent interaction. Solubility in THF, the tetrahydrofurans, or methanol is usually much closer to ideal, so the solvents are used to aid dissolution in the initial test. Different physical form of a compound will have different solubility and dissolution rate. So choosing a particular physical form to ensure bioavailability is one strategy for successful development. I think that's all this presentation. I hope you can understand. If you have something issue to be discussed, please contact me by WhatsApp, or also you can return an email to my email address. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.